Hi, everyone. My name is Nathan Wagner. This is my Hello World video submission to the Happy YouTube channel, where I'll kind of discuss my research. In particular, I'm going to talk about weighted estimates for the Bergman and Szegő projections. And I'll mention that all of this is joint work with Brett Wick at Washington University, who's my thesis advisor, as well as Zhang-Hui Guo and Cody Stockdale. And you'll be able to see on the various theorems who is collaborating with whom. But in general, these are the individuals that I collaborated with during my thesis work. And a little bit about me first. I'm currently a fifth-year PhD student at Washington University in St. Louis. I am scheduled to receive my PhD in May 2022, and I'm currently applying to postdocs that will begin in the fall of 2022. So I thought I would make this video to get my name out on the Happy channel. My thesis advisor, as I said, is Brett Wick. And my research interests include harmonic analysis, obviously, but also several complex variables and operator theory. And in particular, I'm very much interested in sort of the interface between those three subjects. And that's what I would like to talk to you about today. Okay, so let me just start with some definitions about the function spaces that we're going to care about. So if we have a domain in N, so we're working in several complex variables here, the Bergman space A2 consists of the holomorphic functions on B that are square integrable. So this following integral is finite, and dd here is just Lebesgue measure on Cn identified with R2n. And of course, if you raise this to the 1/2 power, this integral, you get the L2 norm. And then in that norm, it's straightforward to show using the mean value property for holomorphic functions. You can show that A2 is a closed subspace of L2. And then just by basic Hilbert space theory, you know that anytime you have a closed subspace in Hilbert space, you have an orthogonal projection. There exists an orthogonal projection, in this case from L2 to A2. And this operator is called the Bergman projection. You can also show using the Riesz representation theorem from functional analysis that you actually get an integral representation of the Bergman projection. So the Bergman projection applied to a function f can be given as integration of the function f against this kernel bd of zw, and bd of zw is called the Bergman kernel, and it's what's called the reproducing kernel for A2, aptly named because it reproduces the values of functions in A2. Okay, so we have an operator with an integral representation, so it makes sense that we might want to apply some harmonic analysis to it. Another space that we care about is called the Hardy space, and we'll denote that by H2 of the boundary. And the way you can think about the Hardy space in this generality is you take the following closure in L2 of the boundary of your domain. You take the closure of the set of functions that are restrictions to the boundary of functions that are holomorphic on the domain and continuous up to the boundary, right? So you're sort of looking at boundary values of holomorphic functions in some sense. And then again, for the same reasons, we can form an orthogonal projection from L2 to H2, and that's referred to as the Cauchy-Szegő, or simply the Szegő projection. And this operator also has an integral representation. So now it's an integral on the boundary instead of the integral on the inside of the domain. And we integrate f against this object SD of ZW, which is called the Szegő kernel. And we're using mu here to denote Lebesgue surface measure on the boundary. I would like to use sigma, but later I'm going to be using the letter sigma to denote a weight. So unfortunate notation there, but and I'll just say that this integral, it makes sense if z is inside the domain. There's a way to associate boundary values with values of functions on the inside for the Hardy space. So there's a correspondence between the Hardy space on the boundary and holomorphic functions on the interior of the domain using the Poisson extension. And so this integral really makes sense if Z is inside the domain. If you want Z to be on the boundary, you have to interpret this as some kind of singular integral. And so what I've really been studying is the mapping properties of these operators. So by their very definitions, it's clear that they map L2 to L2, right? But it's of interest to determine whether they map LP to LP for P in the reflexive range. As harmonic analysts, we ask this kind of question all the time for singular integral operators, Calderon-Zygmunt operators, things of this sort. An example of kind of a function theoretic reason of why you might care about this. If the Bergman projection is bounded on LP, you can say that the dual of AP is AQ. Where here I'm letting Q denote the polar conjugate to P. And I didn't define the spaces AP or AQ, but you can imagine what they are. You just look at the holomorphic functions on the domain and you take the P norm or the Q norm instead of the 2 norm, right? And that will give you a Banach space of holomorphic functions. And these are also called Bergman spaces, but it's the special case P equals 2 where you have a Hilbert space. And this isn't always guaranteed to happen. So for example, there are actually domains for which the Bergman projection is only bounded for P equals 2. So the boundary geometry of the domain really bears heavily on the answer to this question. So let's talk about what people have done in terms of the LP regularity of these operators. If you just look at the Szegő projection, in the case where your domain is a unit disk, the Szegő projection there is often called the Riesz projection. And the boundedness of that in LP is a classical result due to M. Riesz. The behavior of this operator is essentially the same as the behavior of the Hilbert transform on the circle, which we know is bounded on LP. In the case of the Bergman projection, for the disk, I guess this was done by some people in 1964. The general case, when you look at the unit ball rather than the disk, that was handled by Rudin and Forelli in a 1974 paper. And they used Schur's tests for integral operators with positive kernels. So they actually looked at the operator with the Bergman kernel replaced by the absolute value of the Bergman kernel and proved estimates for that operator. That's something that's kind of unique about the Bergman theory. You get equivalent results for the positive operator and the operator. That's very different from other Calderon-Zygmunt operators. You can also look at what are called strongly pseudoconvex domains. So strongly pseudoconvex, well, pseudoconvex just means they're domains of holomorphy. That's the sort of the maximal domains for holomorphic functions and several complex variables. Those are the ones we want to be studying. Strongly pseudoconvex means you have like a strictly positive definite condition imposed on the complex Hessian. Okay, so second derivatives of the defining function for the domain, and it's smoothly bounded, so the boundaries are seen to be manifold. And those estimates were proven by Fong and Stein in 1977. For the Bergman projection, you can look at a bunch of domains that are pseudoconvex and smoothly bounded, but aren't necessarily strongly pseudoconvex. So they kind of have nice boundary geometry, but not necessarily strongly pseudoconvex. Examples include convex finite type, decoupled finite type, or pseudoconvex finite type in only 2 complex dimensions, all smoothly bounded. If you sort of want to think of a motivating example for all these classes of domains, the unit ball is going to be an example of all of these. Okay, so that's kind of the prototype from which all this arises. Okay, and another thing you can do is instead of looking at these kind of other types of pseudoconvex domains, you can keep focusing on strongly pseudoconvex, but lower the regularity boundary. And the minimal regularity is C2 because the condition for strongly pseudoconvex involves second derivatives of the defining function. So this is the best possible result for strongly pseudoconvex domains. It's called the minimal smoothness case, and the LP regularity for P between 1 and infinity of the Bergman and Szegő projections was established by Lanzani and Stein. for these domains. Okay, so that was unweighted LP theory. Now let me talk a little bit about weighted LP theory, and this is going to somewhat resemble the AP or McNiel class in harmonic analysis, but a little bit different. So in 1981, Bekolle-Bonami completely characterized the weights for which the Bergman projection is bounded on weighted LP for the unit ball. Okay, and how do we define these weight classes? Well, Bekolle-Bonami got a weight class named after them. We call them BP weights on the ball. And what you do is you look at this condition, which is essentially an AP condition. It's an AP condition with respect to this quasi-metric on the ball that I believe was originally due to Korani, this quasi-distance. And you look at balls in this quasi-metric, but you don't take the supremum over all possible balls. You only take the supremum over balls that touch the boundary. So the radius is bigger than 1 minus mod z. 1 minus mod z is the distance to the boundary. So these are quasi balls that meet the boundary. And so this is kind of like the AP condition, but with a twist. You're only really caring about the behavior of the weight at the boundary somehow. And Bekolle-Bonami's main result is that these weights characterize the boundedness of the Bergman projection on weighted LP. And what's really the key idea here? Well, as you might expect, if you know harmonic analysis, you should view the Bergman projection as a singular integral operator with respect to the quasi-metric that I displayed on the last slide. And then you can use ideas of Calder and Szegő theory, which is, of course, very well developed. The Szegő projection, the correct class should be an AP class. If you think about just the case in dimension 1 of the unit disk, then the behavior is the same as the Hilbert transform. We know that the AP class on the circle is the right class for the Hilbert transform. So that's also the right class for the Szegő projection. So you kind of have this BP class that works for the Bergman theory and this AP class that works for the Szegő projection. And a natural question, and this has motivated a lot of my thesis work, is if this kind of harmonic analysis machinery can be applied to domains other than the ball. And the answer is that it can be. So a key idea in this is put forth in a 1994 paper of McNiel, where he viewed the Bergman projection as a singular integral operator on many classes of domains to establish LP boundedness. And basically, what McNiel's result says is that if you have a smoothly bounded pseudoconvex domain that's either strongly pseudoconvex, convex finite type, decoupled finite type, or pseudoconvex finite type in C2, and again, don't worry about the intricacies of these. The point is that the boundary geometry is somehow nice. You have a quasi distance, so you have a space of homogeneous type structure where the Bergman kernel satisfies the usual size and smoothness estimates for CZOs. So you have a size estimate, the kernel is controlled by 1 over the measure of a ball, and then you have a smoothness estimate where you look at the difference of the kernel at 2 points. You get 1 over the measure of the ball times this distance from z to z prime over distance of z to w to the delta power for some positive delta. Okay, and once we have these, you can just run the usual machinery, right? And it turns out that it takes some work, but you can kind of combine some of Bekolle's ideas with McNiel's ideas. Of course, McNiel applied this to get unweighted LP results. We wanted to get weighted results. So for brevity, we're just going to call this domain D of one of the following classes I talked about on the last slide, a simple domain. And you can define a Bekolle-Bonami class in these domains. How do you define it? Define it the same way it's defined on the ball. But instead of with respect to the Korani distance, which is specific to the ball, define it with respect to this quasi-distance that was constructed by McNiel. And again, you're only looking at balls whose distance to the boundary is smaller than the radius. So these balls meet the boundary. And what I proved along with Zhang Huo and Brett Wick is that if D is a simple domain and P is between 1 and infinity, then the BP condition is sufficient for the boundedness of the Bergman projection on the weighted LP space. And you might ask, well, that's nice, but can we also get necessity? And the answer is you can for the strongly pseudoconvex domains. So that was one specific subclass. And so then you obtain a complete characterization of the weights for which the Bergman projection is bounded. And this substantially expands Bekolle's result because Bekolle's result was only for the ball. I'll also mention that we also have some work where we use more modern techniques of sparse domination and dyadic harmonic analysis to get a quantitative upper estimate for the norm of the projection in terms of the BP characteristic. So the A2 conjecture was really, really important in harmonic analysis, showing that, first for the Hilbert transform and then for a general Calderon-Zygmunt operator that the norm from weighted L2 to weighted L2 is controlled by the A2 characteristic linearly, and you can get something similar for the BP characteristic, the B2 characteristic. So I'll just mention that as well, without specifically stating the result because it's a little bit complicated to write out. Okay, let me talk about another area that we investigated, which was less smooth domains. And the problem on these domains is that you can't obtain, or people haven't obtained strong estimates on the Bergman or Szegő kernel in these cases. So these are strongly pseudoconvex domains, but that are not necessarily C-infinity smooth. And to prove the LP regularity for these domains, Lenzani and Stein use a trick that goes back to Kurzman and Stein. And the idea of this trick is you construct some auxiliary operator. I'll call it T in the case of the Bergman projection, and I'll call it C kind of for Cauchy integral in the case of the Szegő projection. And this really is like a Cauchy integral in that you're using some theory and several complex variables to get an operator that produces and reproduces holomorphic functions. It's in fact going to be a non-orthogonal projection. And you might ask, well, why would you do this? The reason is that the kernel of T can actually be estimated. It's more or less explicit. And then you can use methods from harmonic analysis, such as Schur's test, or you can use the T-of-1 theorem in the case of the Szegő projection. And so how does that help you with your original operator? Well, because the operator T is a non-orthogonal projection onto A2 that produces and reproduces holomorphic functions, you can get the following operator identities, okay? You get TB equals B and BT equals T, and those hold on L2. So if you think about the first one for a second, if I apply this to a function in L2, BF is going to be holomorphic, right? Because the Bergman projection produces holomorphic functions, and then T reproduces holomorphic functions. So T applied to BF is just going to give me BF, right? And that's where the first identity is coming from. The second identity follows from a similar reasoning. And if you add joints, do some subtraction, use the fact that the Bergman projection is an orthogonal projection, so it's self-adjoint, you arrive at this following equation. You get B times the identity minus T star minus T equals T. And notice this T star minus T term, this is sort of measuring how far T is from being in an orthogonal projection, being self-adjoint. And so what would the general strategy here be? You would want to prove that this operator on the right-hand side is bounded on LP. For the case of the Bergman projection, you can use Schur's test for integral operators with positive kernel. In the case of the Szegő projection, they actually have to use the T-of-1 theorem. It's a little bit more delicate. But then you would want to show that this operator here, sort of this defect operator, the identity minus T star minus T, you would want to show that that's invertible on LP using some harmonic analysis and functional analysis. And so the main question we had was, can this trick be used for weights? And the answer is it can. We obtained several results in this direction. The first says that if D is strongly pseudoconvex with C2 boundary, then we can define an appropriate AP class on the boundary using some suitable quasi-distance. And that condition is sufficient for the boundedness of the Szegő projection on weighted LP. And we did this by kind of using general ideas that I went over on the previous slide. Obviously, there was a lot of work involved to sort of adapt this to the weighted theory. But this general idea of using this Kurzman-Stein factorization and proving boundedness and invertibility of various pieces is really key. And in fact, if you assume that the domain has a little more smoothness, you can actually say more. You can say some nice things about this, this sort of error term, C star minus C. So C is, again, the auxiliary Cauchy operator for the Szegő projection. We can show that that operator is compact on weighted LP for weights in AP for P between 1 and infinity. We can also show that the identity minus C star minus C is invertible on weighted LP. And then, of course, you can actually write down this formula for the extension on weighted LP, and it's given as follows, right? You take the Kurzman-Stein equation and then invert that operator. And then we can do a similar thing for the Bergman projection and BP weights for domains with C4 boundary. So here there was a technical obstruction. In fact, the fact that BP weights don't satisfy a reverse Holder inequality turned out to be technical obstruction. But so we were unable to push down to C2, but for C4 domains, we could get some very nice results about, again, this operator T star minus T, the invertibility of this operator, and then you get that the Bergman projection is bounded on weighted LP, and you have this formula for the extension. So that was the work that we did on minimal smoothness. The last type of the last thing that I'm going to talk about is weak type estimates. So it's fairly easy to see that in general, the Bergman and Szegő projections are not bounded on L1. You can just consider them on the unit disk. For the Bergman projection, if you use something called the Rudin-Forelli estimates, which sort of tells you what happens if you integrate the Bergman kernel against a radial weight in various situations, you can see that it doesn't map L1 to L1. You can also show that for the Szegő projection. But you can ask, of course, if they satisfy weak type estimates, which is the usual replacement in Calder and Zygmunt theory for strong type boundedness. And then you can also ask, can you get weighted weak type estimates for like A1 or B1 weights? And in particular, Cody Stockdale and I were interested in doing this on strongly pseudo-convex domains with near minimal smoothness. So this is what I was presenting on in the previous few slides, where we use this Kurzman-Stein sort of factorization trick, this operator theory trick. And using this trick, you can also get weak type estimates, is the point. I mean, again, there's a lot of work that goes into it, but we were able to show that, for example, if D is strongly pseudo-convex and has C4 boundary, and sigma is a B1 weight, we can show that the Bergman projection extends boundedly from weighted 1 to weighted weak L1. And we had an analogous result for the Szegő projection in A1 weights for bounded strongly pseudo-convex domains with C3 boundary. Okay, and so that was all I wanted to say about my work. In terms of what I'm interested in the future, I have a few specific things as well as general interests. One thing I would like to do is push these weighted results for the Bergman projection to the C2 smoothness case, because I think it's probably true. We just have this technical obstruction. It would also be very interesting to obtain the necessity of the AP or the VP condition, which again, I conjecture is true, but there's some problems with using kind of this operator theory of Kurzman-Stein strategy to obtain this. I'm also interested in two-weight inequalities, and you can think about these different ways. One way is you could define these projection operators with respect to a different weight, and then look at their boundedness on LP with a different weight. Or you could have two weighted inequalities, as in the case of like Hilbert transform, where you're going from one weighted space to another weighted open space, different weights. And so I think both of those questions are interesting. And I'm also interested in studying commutators of the Bergman and Szegő projections and getting various results about their boundedness and compactness on weighted and unweighted spaces. And finally, I'm also interested in some questions involving Toeplitz operators, and particularly the compactness of Toeplitz operators. So I'm very interested in sort of the interplay between harmonic analysis, several complex variables, operator theory, and that's what I plan to continue to keep working on. But thanks for listening, and this was my talk.